So welcome everyone in the next session. In this session, we'll talk about now a more interesting topic, which is manipulators. First of all, and specifically, we are talking about manipulators forward kinematics. Now, we talked about kinematics in first session, and we said that kinematics is basically the study of motion without or with ignoring basically all the external forces, so only the internal forces and the internal actually mobility transmission between different joints. And basically this is what we are talking about, the kinematics, and now specific model of kinematics, which is the forward kinematics model. Now, what is forward kinematics? I also mentioned that before. So for forward kinematics, first of all, and in general, when it comes to robotics and when it comes to robot arms, we have first the reference point. And this reference point is also called the end effector, which basically represents the position of the gripper, let's say, of a robot arm. Now, forward kinematics is basically the model of the position of this end effector as a function of the input variables for all the joints. What are the input variables? So these input variables are the joint variables. So we have seen here that for different type of joints we have variables, right? Which basically these variables could be considered as inputs and could be considered as controlled variables by the actuators. And this basically, for example, if I have revolute joint, it would have only one variable, and of course it is 1 degree of freedom, and in this case it would be theta. And if I have prism, then it would have also one variable, which is S or delta S, basically that representing also 1 degree of freedom. So the forward kinematics, again, is the model of the end effector position with respect to these variables. So if I change these variables, of course, the model position would change. Now we'll see that later also as well, but the inverse kinematic is the inverse direction, which means it is actually the model of the variables. So let's say all the rotational angles are the function of the end effector position. Okay, so which is the more complicated case, I would say. And in order to reach the inverse, we need to start with the forward model, then we can inverse it. So let's talk now about the forward model. I talked about this. The robot's manipulator has typically a combination of revolute and prismatic joints. The manipulator has an open loop mechanism, which means, first of all, it's not necessarily has 1 degree of freedom. Because I also mentioned that if you have closed loop, that means it has 1 degree of freedom. Here we have an open loop because the end effector is actually not connected back to the frame or to the base. So all the assumptions about the loop closure equation cannot be applied here. Now the position analysis, and after that the velocity and so on for manipulators, considering the high degree of freedom that it has, which means it's more complicated position analysis, and to use the graphical or analysis, or let's say the algebraic analysis, is harder. There is a simpler, let's say, form or way to analyze a position of for example end effector, which means basically to analyze forward kinematics, is by using matrix transformations. And these transformations, if you know 3D graphics, you would know these 3 famous transformations, which are scale, rotation, and translation. So a very important thing to consider when it comes to robotics and manipulators, which is the Euler angles. So in the 3D Cartesian space, we have angular velocity, which I said is a vector quantity. It is a vector quantity because it's basically represent rotation around 3 different axes. For example, rotation around X, rotation around Y, rotation around Z. And by these 3 rotations, I would get the angular velocity of this object in the 3D space. So that means we have the total angular velocity, which is projected on 3 axes. Now, this is basically the angular velocity, but it's not a vector in a way that basically it obeys completely the laws of vector algebra because because their order of summation, for example, is not arbitrary. Now, basically, we can describe rotation of an object in 3D space in 2 ways. Either the reference coordinate system is fixed and the object is rotating, which is rotating around x, y, or z, or 3 together. Or basically, the body is fixed and the reference axis is rotating. Now, more on Euler angles, which is basically Euler angles are 3 angles that are representing a rotation of object in 3D space around 3 axes, which is basically they are represented by theta, phi, and psi. Now, these 3 angles actually they represent 3 rotations, but Euler or Euler angles consider that in order to reach any position in 3D space, basically rotational position, not translational, you need to rotate only around 2 axes. So you can use only 2 axes to actually basically reach your goal or your target rotation. And these basically 3 angles represent rotations around 2 axes only. Now, there is an important thing to consider that if you want to achieve your target, you should consider one of these orders, which means that you rotate around z with, for example, theta, then you rotate around x with phi, then you rotate around z again with psi. So as you have always, the first axis is your last axis, and the middle you have another axis. In this way, you can always reach position in a 3D space. Now, so I'm just here have these slides, no, they're not PDF because you can see these rotations here. Just a second.
Another. So when the parts slide around,
oh, there is a voice. So what we are seeing here, basically 3 examples of Euler angle. You need to focus one by one because otherwise you will be lost. So let's look at this one. We have an object that would rotate around z first of all. So then it, of course, here the sign or the whether it's phi or psi is not important, but then it rotates around x, and again it rotates around z. Okay, and in this way it got to specific orientation. So first around z, which basically always would be considered with psi, then rotation around x, which is basically considered by phi, and we have the rotation around z again, which is another, which is basically, let's see, delta, which is basically another psi I would consider. Now here we have another example which is used for airplane, and they are known as basically the 3 angles to have rotation. So we have again the airplane also, you can achieve that with 2 axes only. And why it's important to use it 2 axes? Of course, if I use 2 instead of 3, then I have less motor that I can use, right? So I have 2 rotational motors only that can give me basically the target orientation, which is basically, of course, which means that I can only use 2 degrees of freedom, not 3 rotational degrees of freedom to reach my target location. Okay, so now back to the PDF because it's more clear, the formulas there. So I talked about the matrix transformation, and let's take now, so we have seen here how it's visually, it's basically rotating. Now let's see how mathematically it happens. We take here one example of three orders, or one basically, three orders of rotation. We, for example, start with Z, X, then Z. That means we have three successful sequential, basically, rotations. And for this basically three, we would have three rotational matrices or three matrix transformations. Now the first basically transformation matrix, so we have here multiplication. So transformation is always multiplication, where we have first on the right side is the current, so the position basically of the point with respect to the current coordinate system. Okay, or you can consider is, as I said, it's either we say that the body is fixed and the coordinate system is moving, which means we are transforming the coordinate system, or we could consider that the coordinate system is fixed but the body is moving, or the object moving. So this is a point, let's say, so which is represented by r, the vector r, x1, y1, z1. So this is basically the first position in the 3D space of the point. Now if we multiply this vector with the transformation matrix, it would have a new rotation, so it would have a new position in the space, and this position is because of the rotation around the z-axis. Now the rotation around z-axis here is expressed by cosine theta minus sine theta, sine theta, cosine theta, and then we have 0, 0, 1 and 0, 0. In the next slide we see how we can derive this transformation matrix, but it's important to know that the transformation around z, or the matrix transformation around z, is different from x, for example, which it has same somehow this block but shifted. So we basically have cosine here, minus sine, sine, cosine, and of course it's important to consider that here we have phi, which is basically different than theta, so it's different angle. And then we have here psi, which is third, which is again rotation around z, so we have z, x, z. So in this case we have three rotations, and if I want to apply the three rotations, basically I need to have to, first of all, let's say I first make my first multiplication as you see here, and so let's see what, so we have here the rotation around z. So we have x prime, y prime, z prime, which resulted in x2, y2, z2, and x2, y2, z2 is multiplied by rotation around z, and we have x1, y1, z1, which is basically multiplied by this to get to x, y, z. What's the meaning of that? The meaning of that is this basically the actually the original position, and this is my target position, and to achieve this 3 we need to multiply this with this and this. So this is basically the last one, which is multiplied by the original position, and these are the one before. Right, so basically here we just explaining how we can derive the new orientation, or basically how we can derive this transformation matrices. Now if we have a point in 3D space and two reference coordinates, so the second system rotated around axis of the first, which means in this case the point is fixed in the space and the coordinate system is rotating. Now the point, it is the point itself, so the point is not changing, so it's the same point, but it has two different coordinate systems. The x prime, y prime, z prime is rotated around the axis of x, y, z. Now the vector that represents the point position with respect to the original, or to the x, y, z, is r, and this r prime represents its position with respect to x, y, y prime, z prime. Now it is the same point, right? So that means this equal to this. This is our assumption. It is the same point, so it's just the same vector. Now on the left side we put the projection of this vector on x, y, z, and on the right side we put the projection of that on the x prime, y prime, z prime. Now what we are doing here is three dot products basically. The first, for example, for the first, we are multiplying I with both sides of this equation. So we would have here basically I multiplied by I. Now remember, I basically, when it's multiplied by itself, if you have a dot product, the output would be equal to 1. If it's multiplied with the j or k, because it has 90 degree with j and k, that means the output would be 0. So the dot product of I for these two would be equal to 0. And with this to be equal to 1, this is why on the left side we would have our x. Now on the right side we would have I, basically I prime, ij prime, and ik prime. The same thing would apply on y and z. Okay, so here basically these two would vanish and we would get this one, and here these two would vanish and we keep this one, and there we would have the dot products. Now yeah, so this is just basically that the dot product is equal to cosine the angle between them, and as I said, for example, between I and j the angle is 90, which means the cosine is 0, and ik the angle is also 90, so the cosine is 0, and between I itself it's the angle is 0, so the cosine is equal to 1. So here we are basically replacing this with the cosine between, for example, ij prime is the cosine ij prime here, and ii prime, so we are just replacing it with the cosine. And we are saying here, like just to have the matrix form, is that our x, y, and z is equal to the prime multiplied by the transformations that can be applied to, for example, change the orientation or the coordinate system from that to the original coordinate system. Okay, so now we have what we are doing basically. Let's see if I have rotation around the z-axis, and this rotation is with angle psi. Now what you want to do is, for example, let's say I'm rotating around the z-axis only. Okay, so this here the list of basically the angles that are basically the enclosed angles between the unit vectors, and this is what would result if I consider only rotation around z, which we see it here. So if I'm rotating around the z-axis, then I would have basically psi here, which is the angle between actually x and x prime, which means it's the angle between I and I prime, the unit vectors. So this is why this we can replace it with psi. Okay, now regarding ij prime, which is basically the angle between x and y prime, so this is basically all this angle. Now what we are saying here is that this angle is actually equal to 90 degree, which is this one, plus psi. Okay, so this is basically ij, which is 90 degree plus psi. And if I put cosine the 90 plus psi, phi here, so basically phi, I'm getting minus sine phi. And now regarding now the next one, which is ik prime, which is this is I and this is k prime, right? And it is basically so this is I and k prime. Now z and z prime here are the same axis because we don't have rotation that would change z from z prime, so it is a 90 degree, and this y would have 0, so cosine of 90 would be 0. Now here is basically would be the j I prime. J is this one, I prime is this one, which is in 90 degree minus phi, which will result in sine of phi, and there would be j prime, so this basically which is actually phi. Okay, so cosine phi. Now the rest would be either zeros here because of the 90 degree, or 1 because of the 0, because as I said z and z prime, they are the same. So this is how we derive the first transformation matrix, which represent rotation around Z. Now the next would be basically is if you want to apply this for other transformation, it would be same. Let's say I want to rotate, to describe rotation around Z X only, then I need to see what the angles would be between these different unit vectors and derive here, which would result, for example, in that. Okay, so it's not that different. Now if I want to do sequential transformation like x, y, x, for example, then I need to do multiplication, as I said just before, of different transformation matrices. So for example, here we have two matrices, so we are basically multiplying their transformation, which will we get to the final transformation matrix, which is basically mapping x2, y2, z2 back to x, y, z. Now I can have three basically sequential, and here we are just adding more, which would basically end up with x, y, x prime, y prime, z prime, which basically would drive it back through the three rotational to x, y, z. Now translation is much simpler. It's basically translation where I translate or make actually displacement, linear displacement along x, y, or z, which could be basically represented by this transformation matrix, where so basically we have here diagonal matrix as a part, and this column represents the translation along x, y, and z. Okay, now I will conclude this session, because next session we'll talk about something very important for fluid kinematics, which is called the DH parameters or DH table, or the Navitt basically Hartenberg parameters that can be used to do forward kinematics modeling of a robot arm. Thank you.